Okay, now I would like to explain about the problems on induced EMF, that is dynamically induced EMF and statically induced EMF. So first one, a conductor 1 centimeter in length is parallel to z-axis and rotates at a radius of 25 centimeters at 1200 rpm. So find the induced voltage at the radial field is given by B bar equals to 0.5 into AR bar. So here the B bar equals to 0.5 into air bar, this is constant value, and conductor rotating with a speed of 1200 rpm. So here type of induced EMF, dynamically induced EMF. So here conductor rotating and magnetic flux is stationary. So E bar equals to V bar cross B bar. Here V bar is linear velocity. So in 1 minute there are 1200 revolutions. So given conductor speed equals to 1200 rpm. So 1 minute number of revolutions equals to 1200. So 1 second number of revolutions equals to 1200 by 60 equals to 20. In one revolution, the distance to travel is 2 pi r. A circle circumference 2 pi r meters. Here number of revolutions equals to 20. So the total distance traveled in 1 second equals to 40 pi r meters. So the conductor rotates in pi direction. Hence the linear velocity is given. Okay, velocity equals to distance by time. Here distance equals to 40 pi r, time equals to 1 second. So 40 pi r by 1, 40 pi r, direction a pi bar. So the linear velocity V bar equals to 40 pi r into a pi bar. So given radius equals to 25 centimeters. So 25 into 10 to the power of minus 2. So finally V bar equals to 31.416 a pi bar meters per seconds. So next one, the electric field intensity is given by E bar equals to, so E bar equals to V bar cross B bar, this is V bar, and B bar, okay, given B bar equals to 0.5 into AR bar. So E bar equals to, so V bar cross B bar, here A pi bar cross AR bar, A pi bar cross AR bar equals to minus AZ bar. So electric field intensity equals to 15.708 into minus AZ bar. So next to the induced EMF. Induced EMF E equals to closed line integral E bar dot dl bar. So here conductor lies on z axis. So the differential length dl bar equals to dz into az bar. So E equals to integral E bar equals to 15.708 into minus az bar. So next one dl bar equals to dz into az bar. So differentiation with respect to z, conductor length is given 1 centimeters. So z limits, z equals to 0 to, so 1 centimeters equals to 0.01 meters. So limits are z equals to 0 to 0.01. So finally, so E equals to minus 15.708. So integral dz equals to z, limits 0 to 0.1. So it equals to minus 157.08 millivolts. Here negative sign indicates the upper end of the conductor is positive while lower end of the conductor is negative. Okay, next problem. A circular loop conductor lies in plane z equals to 0 and has a radius of 0.1 meters and a resistance of 5 ohms. Given B bar equals to 0.2 sin 10 to the power of 3 into t az bar. So determine the current in loop. Here we have to find the current. So first to find induced EMF. So next induced EMF by current equal, induced EMF by resistance equals to current. So to find the current in loop, let us first calculate the induced EMF. A circular loop is in z equals to 0 plane. So B bar is in z direction, which is perpendicular to the loop. So B bar is perpendicular to the circular loop. Here B bar equals to 0.2 sin 10 to the power of 3 into t. So B bar is varying with respect to time. So here time varying field. Okay, type of magnetic field time varying field, and conductor stationary. So type of induced EMF statically induced EMF. Okay, this is the circular conductor. So radius equals to 0.1 meters. So the total flux is given by pi equals to surface integral B bar dot ds bar. So assume cylindrical coordinate system. In cylinder, here the loop is normal to z axis. So the differential surface area normal to z axis formula r into dr d pi az bar. So pi equals to surface integration means double integration So B bar equals to given 0.2 sin 10 to the power of 3 into t az bar dot ds bar equals to r into dr d pi az bar. So pi limit 0 to 2 pi, r value radius given 0.1 meter, so r limit 0 to 0.1. So pi equals to here az bar dot az bar equals to 1, 0.2 sin 10 to the power of 3 into t. So first integration with respect to pi, second integration with respect to r. So integral d pi equals to pi, integral r into dr equals to r square by 2. So pi equals to 0.2 sin 10 to the power of 3 into t, 2 pi minus 0 2 pi, 0.1 square by 2 minus 0 square by 2. Pi equals to 6.283 into 10 to the power of minus 3 sin 10 to the power of 3 sin 10 to the power of 3 t. So pi equals to 6.283 sin 10 to the power of 3 into t milliwebers. So the magnetic flux. So here type of EMF, statically induced EMF. The statically induced EMF formula E equals to minus d pi by dt. So it equals to minus d by dt. Pi equals to 6.283 sin 10 to the power of 3 into t milliwebers. Okay, substitute pi here. So by differentiating this equation, so finally we get induced EMF equals to minus 6.283 cos 10 to the power of 3 into t volts. So next find current. So current equals to induced EMF by resistance. In problem given, resistance equals to 5 ohms. So induced EMF by resistance equals to current. So I equals to minus 1.2567 cos 10 to the power of 3t amperes. Here first one, the dynamically induced EMF. Dynamically induced EMF formula E bar equals to V bar cross B bar. So next one, statically induced EMF. Statically induced EMF E equals to minus d pi by dt. So here first to find the velocity, linear velocity V bar. So next by using V bar, we can find the induced EMF. Okay, electric field intensity. Again we can find electric field intensity. So next by using this electric field intensity, so find the induced EMF by using this formula E equals to closed line integral E bar dot dr bar. Here capital E bar electric field intensity, small e is induced EMF. So next one, so next problem. Here in this case the conductor is stationary, magnetic field is time varying. So type of EMF, statically induced EMF. Here first to find the magnetic flux. So next to find induced EMF. The statically induced EMF equals to minus d pi by dt. So next one, current. Current equals to induced EMF by resistance. Okay, in first problem is 25 centimeters is armature radius. Okay, radius. With this radius, conductor is rotating with a velocity of 1200 rpm.